So far what we have seen is that your hydrogen atom has only one electron. When we're looking at orbitals of the same principal quantum number n, the orbitals have the same energy. So if n is equal to 3, then your 3s orbital, 3p orbitals, and 3d orbitals would have the same energy. However, this is not true for atoms with more than one electron. And so here we have an orbital diagram of a multi-electron atom, where if n is equal to 2, then your s and your p orbital have different energy levels. And this is because there's more than one electron, and the electrons do interact with each other. According to Coulomb's law, there is an attraction and repulsion between particles. If there are particles of the same charge, meaning negative negative or positive positive, then the potential energy is positive and decreases with distance. If particles have the same charge, then they repel one another. This is opposite when there are particles of opposite charges. They have a negative potential energy, and this increases with less distance. As two particles of different charges approach each other, they attract each other. And this effect is of a greater magnitude if the charge of the particles is also different in magnitude. So for example, a particle with a +2 charge versus a particle with a -2 charge will have a greater attraction compared to particles of a +1 and -1. Here we have an atom where we have the protons and neutrons in the middle, and we have the electrons on the side. And yes, this is a Bohr model, but to simplify what I'm trying to talk about, we're just looking at the Bohr model, in that the electrons that are closer to the nucleus will be attracted to the nucleus because you have your positively charged nucleus and your negatively charged electrons. And because the electrons in the first energy level are essentially shielding or repelling the other electrons, then the electron that's in the second energy level will be less attracted to the nucleus. So you have an attraction force here attracting towards the nucleus, and here as well. But then you have an opposing force, a repulsion from the electrons that are in the lower energy level. So as a result, if you look at here, and we're looking specifically at the electron here, okay, you have a +4 charge from the nucleus, and it's shielding by 2 electrons. So it has what's called an effective nuclear charge of +2. So there's an attraction of +2 for this electron because the electrons from the lower energy are kind of blocking the positive charge from the nucleus to the outer electron. Basically, if the electrons are closer to the nucleus, they have lower energy. If we look at this radial distribution graph here, where the x-axis is the distance from the nucleus, and on the y-axis we have the radial distribution function. So what that is the probability of where the electron will be relative to its position from the nucleus. So if we look at an s orbital, the electron has the probability of having a distance so far from the nucleus, if we're looking at the s orbital. If we're looking at the 2p versus the 2s, you would think that the 2s has more energy because it's furthest away from the nucleus. However, because you have a probability of what's called penetration, meaning the probability of the electron being somewhere where this electron that we're talking about is somewhere in this location, because remember that it's a distribution, then the electron does not experience shielding if the electron is in this region right here. If there was no electron in the 1s orbital, then the energy of the 2s orbital and the energy of the 2p orbital would be the same. However, because we have an electron in the 1s orbital, we have shielding from a nucleus when we're looking at the electron in the 2p orbital. So again, it's like there's an electron here. We're talking about the electron in the 1s orbital is shielding the electron in the 2p orbital, where in the 2s orbital there is the possibility that the 2s orbital would be somewhere in that location that is not being shielded by the other electrons. So again, I'm just going to go over that one more time. You have the 1s orbital, you have the 2s orbital, and you have the 2p orbital. And so because there is an electron in the 1s orbital, it is shielding or repelling the 2p electron from the nucleus, having a lower nuclear effective charge. Where if there was no electron in the 1s orbital, then the electron in the 2p orbital would not be shielded and it would have the same energy as the 2s orbital, because the 2s orbital has the possibility of being in this region and not being shielded.